Hello guys, hello, how are you? I hope you guys are doing well. I just have to stream at this hour, just because we couldn't stream during the day, but yeah, I see some of you are still awake and connected, which is quite cool. But anyway, most of you are gonna see this video as a recording, so it's still okay. It's still good. I hope you guys can hear me. I hope you can hear something from this side. Okay, so what we're doing today is just going through a few questions on sound waves, superposition, and standing waves. So you have looked at waves before and characterized or seen the different characteristics of waves, which are basically what we have come to know as amplitude, frequency, wavelength. What else do we know? We've got maybe if we have a wave like this, then we can define it in terms of different parameters, where we say the amplitude is the maximum displacement. It's the maximum displacement of the wave, right? It's the maximum displacement of the wave from the rest position. So in this case, this is the rest position, the principal axis of the wave, and the maximum height or the maximum displacement. Usually we use y for this axis. So that maximum displacement in the y. So it can be positive in this case, or it also can be negative. So whatever the case, that displacement is generally given as the A, where A is what we call amplitude, right? And now between successive crests, you can have another feature that you have also looked at, which we call the wavelength. So that distance between points of successive points of the same phase. So that wavelength can be from crest to crest. In this case, that's the crest to the next crest successively, or it can be from trough to the successive trough, or it can be from this phase point to the next point of the same phase. So take note, the phase at this point, let me call it X, is the same as the phase at this point Y, because the wave is moving in that, with that phase at that point. So it's different, it's opposite to the phase at this point Z, where we have got a phase in that direction. So that's a completely a point of opposite phase. We call that, we will say X and Z are in antiphase. Okay, so that's basically what we have in terms of the wave's amplitude, lambda. We can define frequency. If in this case, we've said this is lambda because we are giving our wave in terms of distance moved by the wave. The distance, remember, the wave is designed, or is a mode by which we propagate or dissipate energy from a certain source. So the energy is dissipated through that kind of profile. And as such, we can draw the movement of the wave, of the propagation of the wave, in terms of its displacement versus distance. So displacement is its variation in the y versus distance in the x. So this is one way of presenting it, or it can be the same displacement versus time, where the period between, or the period of one oscillation is what we call, or the time of one oscillation, which is given by 2 pi, is what we call the period t, and the frequency is 1 over that period, such that we get also the relationship velocity is wavelength times frequency, which is basically wavelength for distance and frequency for 1 over time. So that's distance over time. This will give you the velocity. Lambda, the units are meters. Frequency, the units are per second, hertz. So the velocity is given in meters per second. All right, okay, so that's basically what we can say is generally what we have looked at before. And one more interesting thing is we represent this wave, a wave of this form. So I've drawn something like a sine wave here. So this wave will be characterized by the amplitude y at any time t is equal to a sine kx minus omega t. So this is for a wave moving. This will be for a wave moving in the negative x direction, right? So if we would say this one is moving in the positive x direction, then it's minus kx plus omega t minus kx. So we can even write it like omega t minus kx. That's for a wave moving in the positive x direction. Then that means you should recall omega is given by 2 pi frequency, and k is characterized by 2 pi over lambda, right? So what we have in this phase is generally the angles, where omega t is the angular frequency multiplied by t, it gives us the angle, right? Then kx is also the product of the wave number times the distance moved by the wave. So that also gives us the phase difference. So that becomes the phase difference, or the initial phase at time t equals to 0. Okay. So remember, whenever you see an expression like this, then what we have there is the amplitude. Then here inside there is the angle given by omega multiplied by the time t and given by the wave number multiplied by the distance x. Okay. So if you can remember that, then you will enjoy this section on waves. Okay, so I'm sure the audio is good. Just testing on the audio, so that should leave us with everything in order. So I'm just gonna start with the first question. Let me just see if I can just twist something on my screen a bit. Okay, I think we can proceed. That was just setting up this window where you see the working on the whiteboard. So I think that should be clear enough now. So our first question for today is question number 1 from Tut number 9. That's Tut9 on Moodle for PHYV. And the question goes, a boat sounds a fog horn on a day when both the seawater and air temperature are 25 degrees Celsius. The speed of sound in seawater is 1,533 meters per second. How much earlier in seconds does a dolphin 1,000 meters from the source hear the sound than a person in a boat that is also 1,000 meter distance? Ignore the time it takes for the sound to reach the water surface. So this is a question where we have, let's say we have a boat there. And 1,000 meters away is another boat. And at the same point, that's where we have something like a dolphin. So the horn is sounded from this boat, boat A, boat B, and the dolphin are the sides where the sound reaches some time later. So from boat A, the sound would propagate through air at 25 degrees, and we also have water at 25 degrees Celsius. So the sound just goes directly through air, and the sound would also go into the water and propagate through water to the dolphin. So we would neglect the time it takes for the sound from this horn to get to the surface of the water, such that the distance between the two is 1,000 meters. So the speed of sound in air at 25 degrees Celsius, V in air at 25 degrees Celsius is equal to 3, that should be 346.3, 346.3 meters per second. And we're given the speed of sound in seawater at 25 degrees is 1,533 meters per second. Okay, so those are that's the information given in this question, and what we need to find is the difference in time in seconds between the instant when the dolphin hears the sound and the person on the boat also hears the same sound. So what is the time lag between the time or the moment the dolphin hears the sound and the person in boat B hears the sound? So now we need to find the time it takes for the sound wave to get to the dolphin and the difference between that time and the duration it would take for the person on the boat to hear the same sound. So take into consideration that the sound is faster in seawater, so the dolphin hears the sound first, and sometime later the man will hear that sound. So over a distance of 1,000 meters with d equals to 1,000, we simply use the simple formula, time equals to distance over speed. So we've got time for B and time for the dolphin. and the distance is still 1,000 meters for both. The speed in air, the speed there is VA, which is 346. So for B, it's speed in air. For that, it's speed in seawater. 346.3. And this is equal to 1,000 over 1533. So that's meters and meters per second, giving us units of seconds. So 1000 over 346.3 would give us 2.89 seconds. And 1000 over 1533, 1000 over 1533, 1000 over divided by, no, not that, 1000 divided by 1533, 0.65 seconds. So 0.65 seconds from the time the horn is sounded, the dolphin will hear the sound, and 2.89 seconds later from the time the horn was sounded, the man will also hear the sound. So the difference in time between when the man hears the sound after the dolphin has already heard that sound is, so we have at 0, t equals to 0, the horn is sounded, then at 0.65, the dolphin hears the sound, then at 2.89, the man hears the sound. So what we want is the difference in time between those two. So that means delta t is equal to 2.89 seconds minus 0.65 seconds. That should give us 2.24 seconds. So that time is 2.24 seconds, and we have 2.24 seconds there. So that's the correct choice. Take note, you need to use the proper speed of sound in air and the given speed of sound in salt water to get this correct value. Otherwise, if you use 340, which is not the speed at speed in air at 25 degrees Celsius, then you might get other values that are to a different decimal place. So this is one way you need to accurately find the speed of sound in air at 25 degrees Celsius. Okay, then question number 2 is about the Doppler effect. So it's a question on the Doppler effect. So for question 2, okay. All right. A car moving at 36 meters per second. A car moving at 36 meters per second passes a stationary police car whose siren has a frequency of 500 Hz. What is the change in the frequency in Hertz heard by an observer in the moving car as he passes the police car? So the speed of sound in air is 343 meters per second. This time is given. So we have a car moving at 36 meters per second. That's passing a police car whose siren. So the police car is the source, which has a siren of frequency 500 Hz. Then now we want to find the frequency heard by the observer in the moving car, which means the observer is moving at 36 meters per second as he passes the police car. So the change as he passes the police car, which is the change between the observer approaching and the frequency as the observer moves away from the police car. So we have our equation. Frequency is F. Frequency is equal to F naught times V minus V plus V observer over V minus V source. So this is the general expression where we would use plus or minus depending on whether the minus or plus, whether the observer is coming towards the source or moving away from the source. So in this case, positive means observer towards source. And negative for source means negative in this case for Vs. So this is positive for V naught. Negative for Vs means source towards observer, right? Whereas the other part where we have negative there and positive there, the negative for V naught would mean observer away from source, and the positive for Vs would mean the source away from observer, like that. So in this case, we are going to consider a case whereby the observer is coming towards source. So we use this one, this top one for the first part, and the next part is when the observer, so that's one. We'll call this one the first case. Then when as the moving car passes the police car, then the observer is away from the source. So then we will follow our next equation with that expression. So that means the frequency of the first part of the motion, F1, is equal to F naught V plus V naught over V minus Vs. So in other words, another way of looking at it is when the observer is approaching the source. When the observer is approaching the source, this has a tendency of increasing the frequency. So we have V plus V naught, which is a bigger number that increases the frequency above F naught. So this is a big number multiplying the frequency and has a tendency of giving us a higher frequency. So as the observer approaches the source, the frequency increases. As the source also approaches the observer, the frequency would also increase. But if the source is approaching the observer, then it is moving in the negative, basically in a negative displacement, because the observer is the reference point. So the source is coming in the negative direction, because the observer will be in the positive direction as it is going towards that source. So the effect of having a negative there means this becomes smaller and it has an effect of also increasing the frequency, right? So that's one way to also remember this particular equation. So now with this, what it means is we have 500 multiplied by the velocity. V is the velocity of the speed of sound, 343, right? Plus V observer, which is 36, over 343 minus V source. So the source is stationary, we put 0 there. Now, after the car passes, we have F2. Okay, excuse me. Okay, so this is the first expression when the car approaches the police car. F2 is when the car passes, and so this is V minus V naught over V plus Vs, which is 500 multiplied by 343 minus 36 over 343 plus 0. So these two expressions will give us the frequency heard by the observer on approach and the frequency heard by the observer on passing the police car. So we can do that calculation together. So that's 343 minus 36, 343 minus 36 divided by 343. That gives us 0.8895 hertz. Okay. Sorry, that's times 500. So that's times 500. So we can have 500 there. Multiplying this gives us 0.895 times 500 is actually 447.5 hertz. Then the other one is when we have positive there, over 343 times 500, which gives us 552.48, which is also 0.5. So now the question wants us to find the change in the frequency delta, F equals to F, we can say F1 minus F2, because or we can just find the magnitude of this, which is F2 minus F1 will still simply give us a change which is negative, implying that the frequency change is a decrease, right? So that will be a decrease in frequency. As you can see, it's from 552 to 447. But the magnitude of that change is therefore 552.48 minus 447.5. That gives us 104.978, which is 105 hertz. So the change in the frequency there is 105 hertz, which is what we have here. Okay, I hope that's quite clear and straightforward. Then our next question, question number 3, says a jet plane has a sound level of 150 dB. What is the intensity in watts per meter squared? Okay, so this is just a short one. Okay, this is just a short question there. So we can say the sound level in dB is also presented in watts per meter squared in terms of the equation beta in decibels is equal to 10 log intensity over I naught, where I naught is equal to 1 times 10 to the minus 12 watts per meter squared. So it's the reference intensity level at I'm sure it's measured at 1000 hertz, right? The reference hearing level for a normal human being at 1000 hertz. So that's the reference intensity. So now we have for 150, dB equals to 10 log the intensity we want in watts per meter squared over the reference intensity 10 to the negative 12. So divide by 10, then take the anti-log, 10 to the power 15 is equal to I over 10 to the negative 12. Then multiply by 10 to the negative 12 both sides. This and that cancel. We've got I in watts per meter squared will be equal to 10 to the 3 watts per square meter. So that's 1,000 watts per square meter. That's 1,000 watts per square meter. So that expression for the sound level in dB is given by 10 log I over I naught, where I naught is the reference intensity given by 10 to the minus 12 watts per square meter. So that gives us that 1,000. You can check the choices there by just clicking check. That will give you, yeah, that will tell you if that value is correct. Okay, question number 4. Question number 4. A point source emits sound waves with a power output of 100 watts. So we have a point source, 100 watts output. And what is the sound level in dB at a distance 10 meters? So we've got the sound propagating from the source, that's 100 watts of energy, radiating outwards in all directions. Like that. Right, so this is energy distributed over a sphere, but the radius, we're told at some point 10 meters from the source, what will be the level of the sound. So this is just one point, which is a fraction of the 100 watts that is spread over the whole surface. So now it means we have got energy, intensity is equal to watts, power, which is power over area. Our power is 100 watts. Our area is given by 4 pi r squared, which is the area of the sphere around the source. So that's 100 watts over 4 pi times 10 squared. 10 squared and 100. So that's 1 over 4 pi watts per meter squared. So this is the intensity of the energy 10 meters away from the source. Now we need to express this in dB. So dB is 10 log the intensity 1 over 4 pi watts per meter squared divided by 10 to the negative 12 watts per meter squared. So what will this give us? Let's see. Let's see what this gives us. Enter. We've got 10 multiplied by function. Do I see log somewhere? Yes, there's log. Go back there. That's 1 over 4 pi. 1 over 4 times pi divided by 10 to the power negative 12. Okay, so this gives us 109 decibels. So the level there, the sound level is 109 decibels, and that's what we see here at D. That's what we see at D. So that should be also correct. If we did everything correctly, yes. Okay, So for question number 5, a sculptor strikes a piece of marble with a hammer. Find the speed of sound through the marble in kilometers per second. The Young modulus is 50 times 10 to the 9 newtons per meter squared, and this density is 2.7 times 10 to the 3 kgs per cubic meter. So the velocity in a solid given by the property of elasticity and the another property of inertia. So V is equal, there's this formula which you should also always remember, whether it's in fluid or in solids. V is equal to the root of elasticity property over inertial property. So if this is in a fluid, this will be the bulk modulus B, and initial property will be the density. So that will be B over density, or Young modulus in solid over the density again. So in this case, we're in solids, we're using this one, Young modulus over density. So V equals to root of Young modulus over density, which is the root of 50 times 10 to the 9 newtons per meter squared over 2.7 times 10 to the 3 kgs meters per second. So kgs per meter cubed, sorry, kgs per meter cubed. So if we take these units, they will still reduce to meter squared per second squared, which is ultimately, this is kgs meter per second squared over meter. That's for Newton per meter squared over meter squared. And this meter squared multiplies with kgs over meter cubed. So this cancels out with the meter cubed to leave a meter, and this meter adds to this one, it gives us meter squared per second squared, kgs cancelled out. So we've got a root of meter squared per second squared giving us the units of velocity. Okay, so now the values, dividing the values there will give us 50 times 10 to the 9, 50. 50 times 10 to the power 9 divided by 2.7 10 to the 3 times 10 to the 3, everything to the power 0.5. That's the root. 4303. So in kilometers, this is 4.3 kilometers per second. 4,303 meters per second. So I think the question says, what's the sound speed through the marble in kilometers per second? And that's 4.3, which is B. That's 4.3. I hope you guys can follow this. I hope you guys are following. If you have any questions, please feel free to get in touch with us any other time, and we can see what we can do. We can see how best we can assist you. All right. Okay, so let's move on to the next question. Our next question is question number 6. That's question 6. So question 6, a speaker is producing 30 watts of sound. At which of the following frequencies would it sound the loudest? So for this kind of question, you should have come across a graph of power, or that's intensity in decibels, dB intensity. right, or intensity level in decibels versus frequency, which basically shows the different frequencies on a log scale, the power that would have the same intensity level. So with the sound level being the same at that, so it's something like a picture like this. So we'd have like a number of those, so it's different at different levels. That will be, so the lines would represent the same energy, the same what how can I put it here? The same loudness. So that will be the same loudness heard for the different frequencies at these energies. So in this case, let's say I think around this this is where we have almost 1,000. Then around here, that could be 500, and around there we could be at around 10. So that's basically on a log scale. So 100 will be there. Then this will be a point at around 10,000 hertz. So that's frequency in hertz. So already we can see that this point is the lowest point in terms of the intensity level. For 1,000 hertz, it is lower than all the other points, but the same point tends to sound the same as points of higher level, higher sound level. So the sound level is given by that Y scale. So points at the higher sound level, including at 10,000, would sound with the same loudness as a lower, as this lower point, this lower sound level at 1,000 hertz. So this is the lowest point, rather than this one though, but we have the, for the given values there, we have 50 hertz, which will be up there, and 100 hertz for the same energy, which will be 100 hertz is still up there, 500 hertz is there, but 1,000 is here and 10,000 is up there. So now what that means is this point, which is a lower sound level, sounds the same as all the other points but having less energy. So given the same 30 watts energy, a frequency at 1,000 hertz would even sound more than all these other points. That's the understanding. For the same energy, a frequency of 1,000 hertz would sound louder than all these other points. So our choice there would be D. So that is based upon the understanding of sound level and how it is affected by this loudness is affected by frequency. So you can check that. I'm sure that gives us 1,000 hertz for this one. So I'm not really sure if there's a calculation that can show this, but I don't think this is based on a calculation. And my understanding is in understanding this kind of behavior for frequencies and sound levels. So if you see something of interest, please feel free to share with us. Another question number 7, a spherical wave has this form. The spherical wave has a form given here, which is given by phi, a function of the radius and time, gives us the amplitude in centimeters as a function of the radius. The amplitude is 0.02 centimeters, measured as a radial function, and the angle is given by a function in sine of 8 pi x minus 2720 pi t. So now the question is, find the frequency of the wave in hertz. So remember what I said earlier, this is just a function showing how the spherical waveform, the waveform changes with both radius and time. So with distance away from the source and the time. It's a spherical wave, so it's gonna be like so, spherically around from the source. Concentric, right? It's gonna be concentric, but also defined by a sine function. Now, to find the frequency is in one of these terms. This is amplitude. So already I know the maximum displacement of this waveform is 0,002 centimeters. So I can simply write amplitude there is equal to 0,002 centimeters. Then this part in meters connecting with x is kx. So kx is equal to 8 pi, 8.00 pi x. So that means k is 8 pi. And remember, k is 2 pi over lambda. And this is what is equating to 8 pi. Such that if we divide there by pi everywhere and by 2 everywhere, we've got 4.00. 1 over lambda is equal to 4.00. So that means 1 over 4 is equal to lambda. And remember, this was in meters. The meters is already shown here. This shows that this is in meters. Okay. So this is a quarter of a meter, which is 0,25 centimeters. Am I right? 0,25 meters, sorry. 25 centimeters or 0,25 meters is lambda. But the question wants us to find frequency. So in the same understanding, if I go further with this equation, I can see something in t there, which is basically omega t is equal to 2720 pi t. So we can remove the t, we remain with omega equals to 2720 pi. And knowing that omega is 2 pi f, which is 2720 pi, I can remove the pi from both. Then I have 2f equals to 2720, and f is equal to divide by 2, 1360. The frequency is 1360 hertz. Well done. So we've done justice to this waveform, and we have our frequency there. So the frequency is 1360 hertz. And what else are we asked? A spherical wave, which is the same wave, the wavelength, we've already calculated it, 0,25 meters. So that's killing 2 birds with 1 stone. Perfect. Our last question for today goes back to the Doppler effect. So that's how we got 1360 there. Omega is 2 pi f, and 2 pi f is 2720 times pi. So it's always, remember always my equation, my very first equation, omega t, anything that multiplies t in that expression should be the angular speed d theta over dt multiplied by t would leave us with, or multiplied by dt. So t is like the dt, the change in time, and the theta over dt is the omega, which is the angular speed. So if we multiply angular speed times dt, we remain with d theta, which is the change in the angle. So this is the angle change, which is d theta. And in this case, this is just the wave number also given by 2 pi over lambda times x. So it gives us a phase, how much of what fraction has been traversed by the how do I put this, by the wave, right? As a function of the wavelength, right? So as x over lambda is a fraction of the wavelength, it gives us the phase position of this, of a complete cycle, right? So if this is x and this is lambda, then when x is equal to a complete wavelength, then it means we've only moved a complete cycle, which is a phase angle of 2 pi. When x is half of the wavelength, meaning x is up to there, then we have x over lambda being half and it's half of 2 pi. It means we've only traversed a phase, we call this a phase difference of pi, right? So it's this part is what we have called the phase difference. It's what we call the phase difference given by the wave number times x. So they all give us angles anyway. At the end of the day, they are all part of what we have as our phase, total phase. So if we equate k there to this, then we can also find lambda that way. All right, so let's look at the last question. I'm sure you guys can work it out now because we've already done something similar. We have a truck moving at 36 meters per second, passing a police car moving at 45 meters per second in the opposite direction now. So this time the police car is moving. And if the frequency of the siren relative to the police car is 500 Hertz, what is the frequency heard by the observer in the truck as the police car approaches the truck? So the speed of sound is still 343. Remember, we said we can find F by using F naught, then V, the speed of sound, plus V observer over V minus V source. This is when the observer is moving towards the source. So the truck is moving at 36, then it passes the police car, which is moving at 45 meters per second in the opposite direction. So the source is also moving towards the observer is moving towards the source. So just in this case 500, 343 plus V observer is 36 in the truck over 343 minus V source, which is 45. And we can solve for that. We can solve for that by entering our open bracket, then the 343 minus plus 36 over 343 minus 45 multiplied by 500. So that's 500 times 1.272 multiplied by 500, you get 635.9. So the frequency is 635.9 Hertz, the higher frequency, which makes sense. So 6.3 is wrong. All these are lower. 6.17 was higher, but the 6.36 is the rounded one by just putting the answer to 3 significant figures. We get 6.36. So that's it, guys. I hope you guys will benefit from this video. Otherwise, for today, that's all we had. You should watch out for more questions that we'll be covering during the course of the week, as my colleagues will take on the rest of the questions to the end. Otherwise, from me and everyone at Yebo Physics, it's goodbye. Keep well and all the best with your studies. Bye.